Hello, and welcome to my presentation on the chemistry of tin. The focus of this presentation is to give some background information on some of the general physical properties of tin and to introduce you to some aspects of the reactivity and structure of its various compounds. Now, in light of the physical properties of tin, it's a general trend that down group 4 we have increasing metallic character of the elements. In terms of tin though, some sources do call it a metal and others a metalloid, so here I'm just going to refer to tin as being a metal. Structurally, tin can arise as one of two allotropes: alpha tin, known as grey tin, and beta tin, known as white tin. And this is actually the most stable form of tin at room temperature. Now, alpha tin crystallizes out in a diamond-like lattice, whereas beta tin does so in a body-centered tetragonal unit cell. Although a lack of sources drove me to bring out this particular unit cell image, which is not the actual arrangement of tin atoms within the lattice of beta tin, but it is the shape of the unit cell in which it may crystallize, whereby each tin atom is 6 coordinate within the structure overall. So we're now going to look at how elemental tin may be extracted and a couple of ways in which we can attain tin in general. This is typically done so by redox reactions. Now, one of the primary routes is to take cassiterite, so tin 4 oxide, and this is the natural form in which tin is found. We take this with some carbon and heat it up, and we form some elemental tin along with some carbon dioxide. Now this, as we can see here, is actually a reductive extraction route. So we're going from the +4 oxidation state of tin here in the tin 4 oxide to the 0 oxidation state in elemental tin. And simultaneously, we oxidize carbon from the 0 to the +4 oxidation state. A second way to obtain elemental tin is by taking this tin 2 oxide with potassium hydroxide, and we go on to form this particular tin oxyanion salt here, along with elemental tin and some water. Now, using a different stoichiometric quantity of the hydroxide in this reaction, we can then go on to yield another tin oxyanion salt in the process. Now, can you spot the reaction type here? Of course, these are examples of disproportionation reactions, right? So see how the tin becomes both oxidized and reduced? I'll show you the oxidation states just to prove the point. Now, as you can see, I've only really shown 3 oxidation states of tin here, but it is worth noting that tin doesn't arise exclusively in these states. It can do so in any state between -1 and +4. We'll see the importance of these variable oxidation states very soon. Now, of course, there are so many other tin oxygen compounds out there that we can synthesize apart from these ones. We're only just really scratching the surface with these examples. Another set of tin compounds I'd like to introduce you to, though, are the halides. The ones we'll be looking at here are tin 2 and tin 4 halides. Do be aware though that other halides such as tin 1 halides do exist. We'll be seeing their applications very shortly. Now, tin 2 halides tend to be like ionic compounds in their nature and tend to have higher melting points via their strong ionic-like bonds. A couple of examples here being tin 2 chloride and bromide, both exhibiting melting points in excess of 200 degrees C. These halides also have the capability of behaving like Lewis acids. Now, introduce a tin 2 halide, accept the fluoride to its respective halide ion, and we create this anionic tin 2x3 species, which, in structural terms, is comprised of chains of these species linked via the halogen atoms themselves. Now, as the tin 4 halides go, these are more covalent based in light of their bonding, and are typically held together by weak London dispersion forces, and thus exhibit lower melting points due to their greater volatility. Taking the chloride and bromide compounds again, we see a drastic difference in their melting points because of this bonding difference. Although what we do see is that these compounds are actually much better Lewis acids than the tin 2 halides, and we see them coming together now with 2 of their respective halide ions for the chloride and fluoride compounds to create these anionic tin complexes, structurally defined as octahedra. Now, all of these discussed types of tin compounds thus far have numerous proposed applications, and even though there are some really interesting ones out there, these utilizations are not the focus of this presentation. And so, continuing with the theme of reactivity and structure, we can instead look at tin cluster compounds. and one of their synthetic routes was actually mistakenly discovered by the Schnökel group, whereby their clusters consist of a greater number of metal atoms in comparison to ligands. Now, as a general route, we can synthesize these compounds via taking a tin 1 bromide/chloride, which I lightly glossed over earlier, with some sterically demanding organic ligands, labeled as SDOLs here. And via disproportionation reaction, we can create these Schnökel-type clusters, along with some of our predefined tin 2 halides. Okay, now it can actually be quite difficult to control these reactions, but they can be done. But more generally, for any group 4 metal cluster that is not a Schnökel-type cluster, we may take this RMX compound with the defined parameters, and via a generalized reduction reaction, we create some form of a cluster. Now, an example reaction product being this octosilycubane, where R is this somewhat bulky ligand. Now, other sorts of tin clusters we can attain via various other synthetic routes can be based upon these so-called ligand-free zintal ions, okay, shown here. Now, we can get these for elements such as tin and germanium, as seen, and we can build upon these zintal ions to create our predefined Schnökel-type clusters, okay? Structurally speaking, it's because tin can attain various oxidation states and bind well to numerous atom types, seen to a slight extent, its clusters can attain numerous geometries and structural types. Now, we can actually determine the structure of these clusters via various crystallographic studies and other analytical techniques as well. For example, take these two clusters here, right? Both of their structures determined via X-ray crystallography. Now, we can actually take this structural analysis a little bit further. Take this Schnökel-type cluster, based upon that ligand-free zintal ion I showed you in the last slide. This is produced by a variation of the monohalide synthesis I again previously showed you, and through X-ray crystallography, we can actually pick out that this cluster crystallizes out in an orthorhombic unit cell. And we can also pick out some nice trends when comparing the bond lengths in this structure to those evidenced in germanium counterparts. This being that as the tin atomic radius is greater than that of the germanium radius, longer bond lengths are observed in the tin cluster in comparison to the germanium cluster. Now, it's a simple trend, but yet something that can express our known knowledge of the elements. Now, from the structure, something else we can also see is that the capping tin atom here, okay, is relatively quite exposed in comparison to the rest of the cluster atoms. And so, by performing quantum calculations based around electron density, we can show that this is actually the most reactive site towards electrophiles due to both its exposure and greater electron density. Now, this image here is simply depicting one of the defined homos of the cluster, okay, showing that the exposed tin atom has this great electron density that we've just spoken about. Interestingly though, neither a mass spectrum or NMR spectrum of this cluster was taken in THF, so the mass spectrum shown here. The cluster actually reacted with the THF in such a way to render the solution nearly void of any of the original cluster. Now, these new compounds were proposed to contain at least one other tin atom within the structure, so shown here, or having an alteration in its ligand count in conjunction with this when compared to the original cluster. The high reactivity of the exposed tin atom could possibly be why the cluster reacted in such a way. Although, taking this cluster in a solution of both THF and 12 crown 4 shown here, enabled the cluster to remain stable within this solution for a number of days. The NMR spectrum of this solution, so shown here, was taken over those numerous days, and it was seen that the relative intensity of the SIME3 peak of the original cluster, so shown at delta 0.08 here, began to diminish, and other peaks, being identified as THF reaction products, started to arise. This still being due to the instability of the original cluster in this solution, however. And so, as evidenced, the determination of the structure of these compounds can be quite interesting, yet quite difficult to gauge at times via taking a reactivity perspective. But there's still so much to discover about these compounds, their possible future use in medicine being one of these development areas. So we're only really just starting to realize the true potential of these compounds. So who knows? Maybe they'll be a big part of the next few decades. But until then, thank you for watching my presentation.